Hello everyone, we're going to continue with Module 16 Part 4, or Lesson 4. This is going to be Part 2. We're going to continue talking about the senses of hearing and equilibrium. So moving forward, we've gone over all of the anatomical structures, all the important ones for this conversation for the ear so far, right? And all of those structures essentially are going to contribute to both hearing and equilibrium. The external and the middle ear are exclusive to hearing, whereas the inner ear is going to be those structures that we're about to break down now in terms of how those are working, and those are contributing to both hearing and equilibrium, separate parts obviously. So let's get right into it. Now, whenever we stimulate those functional units, the actual things that transmit those sound waves into the nervous inputs, right? Those action potentials that will communicate with the central nervous system. Those are those cochlear hair cells, right? And so let's go through real quick a breakdown of what's actually happening. So we've got the vibration of those ossicles, those three small bones. The vibrations of those cause pressure waves in that internal ear fluid. Okay, so we move that fluid. Movement of that fluid is going to cause a vibration of the basilar membrane within the cochlea. And then the hair cells are going to move this membrane. The structure and the arrangement of what we call stereocilia of the inner hairs are basically bathed in a endolymph, right? And that endolymph has high quantities of potassium ions, right? So those charged particles, and this can actually create a gradient from the fluid to the hair cell itself, right? Between the hair cell, inside of the hair cell and the outside fluid. And so whenever you basically have this protein that acts as a ion channel, so a gate allowing those potassium ions in, whenever you expose that ion channel, it allows for that for those charged particles to go from the outside to the inside. And whenever we do that, it's what's going to create a action potential, right? So it's going to trigger a nervous response from that channel opening. And we're using a lot of words here. You're about to see how this works with a visual. But basically, those stereocilium, which we're about to see, they're bent whenever that base membrane rises towards the top membrane, right? That tectorial membrane. This is going to pull on what's called tip links. It opens those ion channels. Potassium flows in. Depolarization causes the release of a neurotransmitter. And that neurotransmitter is ultimately going to stimulate that dendrite of a sensory nerve cell, and it's going to then generate that action potential along the cochlear nerve, and that's going to go to the auditory cortex of the brain eventually. So important to keep in mind, so once stimulated, these hair cells basically transmit impulses along that nerve. This is just a division of cranial nerve 8, and it's going to the auditory cortex that's in your temporal lobe, where you actually interpret the sounds. Okay, so sound usually reaches the two ears at different times. It's pretty cool. This is actually what helps us determine where sounds are coming from in our environment. So like whether they came from in front of us, behind us, to the left or the right. So that's what's actually happening there. So the little delay between left and right ear could give you your sense that it's coming from the left. And when the same sound actually keeps reaching our ears ongoing, right? So maybe just like think about, I would say like the humming or like, you know, a lot of people listen to like white noise and pink noise. Whenever they keep the same sound reaching their ears for a prolonged period of time, those receptors tend to adapt to that exact sound. And so there's no transformational shift in any of the structures and the liquids. And so basically we just can become no longer aware of them. There's no difference in that environment. So that's also a pretty cool thing, that we can adapt and kind of get used to different sounds that aren't just silence and still more or less be at rest without that ongoing awareness. So here's a couple of useful images to show you how this works with actually opening up these gated channels and allowing those potassium ions to flow into those hair cells. And again, that causes a release of neurotransmitter, depolarization, and then an action potential actually sends nervous information to the brain. But basically, you've got all of these channels, right? These little protein channels. Whenever you have fluid move over these tip links, these stereocilia, each of these like hair-like projections, you can basically cause a transformational shift. It pulls on those tip links to open those channels. So basically liquid, this lymph fluid, whenever it is pushed, right? So whenever we get that fluid moving, that is what's ultimately going to cause a shift, opening those channels, and that's how we were to pass that, that initial sound wave into the nervous input. And just wanted to show you that what this pathway actually looks like. You've got your first, second, and third order neurons, but really it's just showing you a process where it goes from that cochlear nerve, right? So we've stimulated that cochlear nerve. It's going to go along this pathway up to that primary auditory cortex, and you're going to have one of these dedicated to your left and your right ears. So what happens whenever you have some sort of a loss of hearing? We call this deafness, right? There are two major kinds of deafness. You've got conductive deafness. This is where basically we interrupt the transmission of vibrations, right? So something is actually blocking those vibrations from moving along the path. This could be a damaged eardrum, a condition called otitis media, blockage of the auditory canal, and then otosclerosis, which is basically those three small bones. They basically fuse together and they can't really vibrate as easily, right? They become more rigid. So that's conductive deafness, where we can't actually conduct it along its normal pathway. Something's interrupting that. And then you have nerve deafness, or sensoroneural, which is death of hair cells, right? Those functional units, we actually have death of those cells. This happens a lot whenever you're frequently exposed to high volumes around you, right? So like factory workers, musicians, construction workers, really speaks to the importance of wearing appropriate hearing protection, especially whenever you're listening to your music, like in your AirPods, like keeping the volume at an acceptable level. I believe there's also settings that you can set up on your phones to make sure that it communicates how loud it is and at what point it's likely to cause some form of mild hearing damage. You want to make sure that you don't listen to your music too loud. And that's because like we have hearing aids, right? These basically use skull bones to actually help conduct sound vibrations to the inner ear. Those will obviously, because it's going to help conduct vibrations, those are going to be really good for conductive deafness, but not so much for sensorineural deafness, right? So if we have that permanent loss of hearing because the hair cells themselves are damaged, that's going to be more or less permanent, right? That's why, you definitely want to take good care of your ears and wear the proper protection. And then we're going to finish up just by covering a couple of the basics whenever it comes to equilibrium, what structures are contributing. Equilibrium is just basically where your body's oriented. It's senses where you're moving, how you remain balanced. Okay, so we basically have the vestibule, or the vestibular apparatus. This is what actually contains your receptors for equilibrium. Okay, extending from these, we do have these three semicircular ducts, right? And two chambers that are within the vestibule called the saccule and the utricle. Okay, now we're going to talk about the semicircular ducts, and those are actually really cool, but we've got two different types of equilibrium we need to know about. Static, which is just basically not necessarily in motion or in rotation, right? So perception of orientation of the head in space. So this is basically giving you your idea of which way is up or down, right? So this is especially useful, let's say whenever you're underwater, right? If you get a little bit deep in the water, you're gonna need this static equilibrium to know which way should I swim when I need to come up for air. Yeah. And this is actually detected by the saccule and the utricle. I'll show you a diagram of that in a moment. And then you got dynamic equilibrium. This is, again, perception of motion or speeding up, acceleration. You have linear acceleration, which the saccule and utricle are specific to. It's just basically anything in a straight line. And then you have angular, which is a change in the rate of rotation. And this is where the semicircular ducts come in. Inner ear anatomy, so I'm going to show you just real quick. So we just talked about, with hearing, we talked about this cochlear duct in the cochlea. We kind of went through all of that and went pretty microscopic to see how that's working. Within the vestibule, this center area here, you've got your saccule and you've got your utricle. So these are going to be what helps with, like, let's say, static equilibrium. And then dynamic equilibrium, you've got this system of semicircular canals or ducts. And the cool thing about these, and I think I talk about this on a slide here in just a moment, but you have these 3 semicircular ducts, and they're in each of the 3 planes of motion. Right, so you've got one that's along your sagittal plane, you've got one along your frontal plane, and you've got one transverse. So any sort of rotation, whether that's front to back or side to side or rotation, you're going to have the ability for that fluid to move and activate hair cells, same as it does with hearing, but just for equilibrium in this case, and it's going to help give you a sense of body motion and your position in space. So we activate by, obviously, again, moving those fluids across hair cells and opening those channels and providing information to the brain. And that's the main structures we need to keep in mind. This kind of shows you the utricle and the saccule here, and kind of like what would happen as this fluid were to be, let's say, moving over or to shift due to rotation or some sort of motion coming into place. It shows you, like, here head is up, here head is down. It causes that gravity shift and in that fluid inside those canals. And then finally, so I included that, the semicircular duct, so any type of rotational movement, we're picking that up by these 3 ducts. Spatial orientation in any plane of motion, which is extremely helpful, obviously. And then each of these ducts filled with a certain type of fluid. And I believe that is as detailed as we need to get into the semicircular ducts. Gave you another really useful image. If you'd like to pause and kind of take a look at this, feel free. But it's just showing, again, we're stimulating hair cells. The exact terminology of these structures is a little bit different, but ultimately the physiology is the same, where we have a transformational shift or a movement of the fluid within these structures, and those movements basically transformational shift of the hair cells and open those ion channels, and then it creates an action potential that communicates information about body position to the brain. And that's going to conclude part 2 of our discussion. So, guys, that is hearing and equilibrium. Again, feel free to review at your leisure, and I hope you found this helpful.